Welcome everyone to Chemical Reactor Design course. My name is Shakir Haji and I'm really excited to teach you this course as much as you are excited to learn. Let's start with lecture 1. In fact, this course is divided to around 50 lectures, and some of the lectures are divided into 2 segments or 3. So let's begin. My favorite question at the beginning of any chemical engineering course is, what are the core subjects of chemical engineering? So can you guess with me what are these core subjects? And I'm not talking about courses as much as I'm talking about subjects. Okay, so you guessed it right. The first core subject in chemical engineering is chemical engineering thermodynamics, which you learn in Thermodynamics 1 and Thermodynamics 2 and part of applied physical chemistry and some other courses as well. This is the first core subject in chemical engineering, and this is where you learn about equilibrium, and this is where you learn about the limits of nature. Then comes transport phenomena, and in fact transport phenomena is divided into 3 subdivisions. First one is momentum transfer, or what is known as fluid mechanics. Then comes mass transfer, or also known as separation processes. And finally you have the heat transfer. So these 3 courses really form what's known as transport phenomena. So transport phenomena is the second core subject in chemical engineering. What do you notice? What's the common between all of these 3 topics? Momentum transfer, mass transfer, and heat transfer. Obviously, you have a conserved quantity that is being transferred at a given rate. And all of these processes are physical in nature. Okay, then comes the last core subject of chemical engineering, that is chemical reaction engineering. That's the third core subject, and it's different from the second one, where it involves chemical changes. The second subject involves physical processes, but the third one involves the third core subject involves chemical processes. And what's the commonality between these 2 core subjects, subject 2 and 3, is that they both depend on rates. So here we're talking about the rates at which the chemical process take place, and in subject 2, transport phenomena, we're talking about the rate at which these phenomena are transported: momentum, mass, and heat. Okay, for example, we talk about how fast heat is being transferred in the heat transfer course. But in chemical reaction engineering, we talk about how fast the reaction is taking place. So these are the core subjects of chemical reaction engineering, and I said every subject involves few other courses. Okay, the second question is, which is related to this course, what do chemical kinetics and chemical reaction engineering involve? Well, chemical kinetics is a subject that you have studied in chemistry and also in applied physical chemistry, is the study of chemical reaction rates and mechanisms. And I'm sure that you have dealt with mechanisms a lot in organic chemistry. And regarding chemical reaction rates, you've studied it in chemistry, applied physical chemistry, and so on. The study of chemical reaction engineering, however, combines the study of chemical kinetics with the design of the reactors in which the reaction occurs. And usually, chemical reaction engineering is abbreviated as CRE. It is primarily the knowledge of chemical reaction engineering that distinguishes the chemical engineer from other engineers. Let's take an example. Let's talk about fluid mechanics. It's a subject that is studied in mechanical engineering, chemical engineering, civil engineering. So it's shared between those disciplines. Let's look at heat transfer. That's another subject which is covered in mechanical engineering and chemical engineering. Everyone's claiming that they invented this subject. However, when it comes to chemical reaction engineering, it is really the subject, a core subject of chemical engineering, and it's really related to chemical engineers. So they are the one who excel in the subject of chemical reaction engineering. Okay, a third question. What does chemical engineering thermodynamics involve? We said the first core subject and the most important one, the one which comes on the top, is thermodynamics. So what does it involve? It involves calculations of heat and work requirements for physical and chemical processes. Of course, we do care about the amount of heat that we can get from a given reaction, for instance. Okay, and we do care about the amount of work that we get from a turbine, steam turbine, gas turbine, or the amount of work that we have to supply to a compressor. Okay, these are very important quantities, and we usually calculate them from the first law of thermodynamics. So that's something which is the business, the core business of thermodynamics. The second business of thermodynamics is the determination of equilibrium compositions or equilibrium conditions in cases of chemical reactions and transfer of chemical species between phases. We have always said, or in the course of course of thermodynamics, in the subject of thermodynamics, we always said that thermodynamics deals with equilibrium, right? So with equilibrium we mean, voila, if you have a chemical reaction, what's the equilibrium of that reversible reaction? Where the reaction stops? What's the equilibrium composition? Okay, and when it comes to physical changes, we're talking about equilibrium and the transfer of chemical species between phases, VLE, right? Vapor liquid equilibrium. If you have, for instance, two species in a liquid solution, and this liquid solution is in equilibrium with the vapor phase, we can know the partitioning, how much of, for example, species A is in the liquid phase and how much of it is in the vapor phase, and so on. And we know that there's an equilibrium between these phases, of course, if equilibrium is reached. So again, that's the business of thermodynamics. It involves the calculation of heat and work, and also determination of equilibrium composition condition in the cases of chemical reaction, chemical changes, chemical processes, and the transfer of chemical species between phases, that is a physical change or physical process. What thermodynamics cannot predict? Very important question. Thermodynamic considerations do not establish the rates of chemical and physical processes. We said the rates are the business of transport phenomena for physical processes, or the business of chemical reaction engineering when talking about chemical processes. Correct? So it's not the business of thermodynamics. What do rates depend on? Usually, what do rate depends on? If you have a rate, what does it depend on? Well, it depends on driving force and resistance. The rate depends on driving force and the resistance of a given phenomena. Although driving forces are thermodynamic variables, like the temperature difference, the pressure difference, the temperature difference in case of heat transfer, pressure difference in terms of flow, the voltage difference in terms of the flow of current, and so on. All these variables, which are the driving forces, are related to thermodynamics. They are thermodynamic variables. But resistances are not. The resistance is not the business of thermodynamics. So although driving forces are thermodynamic variables, resistances are not. And hence, if this is not part of thermodynamics, that means thermodynamics cannot predict rate. Neither can thermodynamics reveal the microscopic mechanisms of physical and chemical processes. So usually when we talk about the microscopic mechanism of a given reaction, for example, that's really not the business of thermodynamics as much as the business of kinetics. Okay, let's take an analogy to what we have just said. Let's assume that we have this ramp. If we leave the ball, I know that eventually the ball will reach to the bottom, right? To the lowest point, correct? When equilibrium is reached, this is where it's gonna be, right? However, if the surface was not really smooth, then still it's gonna reach to the bottom, to the same place, which is the bottom, right, to the lowest point. However, it's gonna take longer time due to the resistance. So how fast this process happens is not the business of thermodynamics, because we're talking about how fast, a rate. And when it comes to rate, you need to know the resistance, and the resistance is not the business of thermodynamics. Therefore, thermodynamics tell you where the ball will stop, but does not tell you how fast does it reach there. You need transport phenomena or chemical kinetics sciences to determine how long you need to wait or how big your equipment should be to reach equilibrium or where you want to be. Tamam? So I hope the picture now is clear. So the rate determines how long we need to wait. Time, if you had a batch process, or if you had a continuous flow process, then we don't talk about time, but we talk about how big the equipment is. Okay, let's take a time out with the generalized equation for flux. So why are we talking about flux? Because flux is a quantity that we can calculate, and it equals rate over unit area, correct? And we care about rates. So that's why we're talking about flux, because rates can be calculated from flux. That is flux equal rate over area. Okay, so rates, we said the rates depend on driving force and resistance. The governing equation for any flux, that is rate over area, can be generalized as J equals M multiplied by F, where J is the flux, F is the driving force gradient, and M is the coupling coefficient, coupling J to F, or what's known as conductivity. Tamam? Or you obviously know that conductivity equals 1 over resistivity. So the flux always equal the conductivity times the driving force gradient. Conductivity times the driving force gradient. Okay, let's take an example. Let's start with the current density. Let's start with the current density. So I know that the current equals the voltage over R, where R is the resistance, right? So R is the resistance, not the resistivity, but it's the resistance. Okay, and I know that the resistance equal rho, which is the resistivity, right, which is the property of the conductor where the current passes through, times the length of the wire, for instance, divided by the cross-sectional area of the wire. Okay, that's the resistance. So you can see that resistance is a phenomena, but resistivity is a property. Okay, so here we're talking about the property of the material, which is conductivity, or 1 over resistivity. Okay, let's go to J double prime, which is the current density. What's the current density? The current density is I divided, which is the current, divided by the cross-sectional area. Okay, and I know that the current equals V over R, right? V over R. So if you substitute this here, you will end up with 1 over rho times V over L. Okay, so let's see this 1 over rho multiplied by V over L. Okay, 1 over rho, which is 1 over resistivity, and is actually the conductivity. And then we have V over L. Or if you want to be more precise, more correct, then the current flux actually equals the conductivity times the driving force gradient. The conductivity times the driving force gradient. And this rule here we just talked about applies to many fluxes. For instance, if we talk about the molar flux, and of course you remember that the molar flux, or known as, you can calculate it from the Fick's law of diffusion, equals minus dAB times dCA by dx, where d is the diffusivity representing the conductivity. Conductivity is how good, right? While resistivity is how bad. Okay, so the molar flux equals Na double prime equals minus dAB, which is the diffusivity representing the conductivity, multiplied by the driving force gradient, right? This is the driving force gradient, which depends on the concentration. So the concentration actually helps you to transport moles, right? Okay, so the difference between the concentration is the driving force, and the driving force gradient is dCA by dx, where x is the traveling distance. The same thing with heat flux. If we have conduction, so Qx double prime is minus K, right, times dt by dx, right? And again, K here is the conductivity when it comes to heat transfer. It is exactly known as conductivity, right? And then the driving force gradient for the heat flux, for the heat transfer, the driving force is the difference in temperature. So the driving force gradient is dt by dx, and so on, and so on. So you always have the coupling coefficient times the driving force, and so on. Whether we talk about heat, right, this form or this form, or the molar flux written this form, okay, which is basically in this case it's the conductance times the driving force. But the original equation is related, the flux here, we're relating it to conductivity times the driving force gradient. Anyway, so now you got a good idea about flux and rates. Okay, and you can see where the resistance coming into the picture. Okay, M, which is 1 over resistivity, and we said this is not the business of thermodynamics, therefore I cannot predict rate using the science of thermodynamics. I hope that this is clear. Okay, so what each science enables you to know then? Well, let's take an example. Let's take this block made of aluminum and its temperature is 50 degrees C, and put it next to another block of aluminum, the same mass, obviously. Okay, so and the temperature here is 100 degrees C, and let's insulate the system. So now what would happen? You guessed it right, heat will start transferring, right, from the higher temperature block to the lower temperature block. So heat will start transferring, right, from the higher temperature to the lower temperature until equilibrium is reached at after a finite time, right, or after an infinite time, very long time. For sure equilibrium will be reached. What's the equilibrium temperature? Well, you need to calculate it, right? How do you calculate it? Well, you will calculate it through the knowledge of thermodynamics, the first law of thermodynamics. Remember, delta E equals input minus output. So the system is insulated, so the change in energy is 0. Delta E equals to 0, no change in kinetic or potential energy, so you end up with delta U equals to 0, and this consists of delta U system 1 plus delta U system 2 equals to 0, where 1 is block 1 and 2 is the second block, and you know how to calculate the delta U. Remember, it is mass 1 times CV1 times T equilibrium, right? That's the final temperature, minus T1, which is initial, and the same thing you write it for second system, T final minus T2. Okay, and all of this actually equals to 0, correct? All of this equals to 0, and you know that mass 1 equals mass 2, so it will be cancelled out. Let's assume CV1 equals CV2, cancels out, correct? And then you have TF minus T1 plus TF minus T2 equals to 0, and then you calculate and you get the final temperature, that is 75 degrees C. So I was able to calculate the final temperature, which is the equilibrium temperature after the system was left long enough for equilibrium to be reached. So we talk about equilibrium, that means I can use the thermodynamic science to calculate the final temperature or the equilibrium temperature, that is 75 degrees C. But the question is, how long should I wait? How long should I wait until this happens? Well, how long you should wait depends on the heat transfer rate, right? Heat transfer rate, how fast the heat can transfer from the higher temperature block to the lower temperature block. And this is not the business of thermodynamics, right? Talk about heat transfer, so it's the business of the heat transfer science, right? So heat transfer subject. Okay, so heat transfer actually help us to calculate how long I should wait until this temperature is reached. For example, I'll tell you we need to wait, let's say, around 3 minutes in order for the temperature to reach, let's say, 74.9999, right? Or 75.0001 from the other side, and so on. So now I hope that's the picture is getting even clearer. Let's take another example, which is more related to our subject. Okay, and we're talking about reactions. So let's look at this reaction. You have to memorize this reaction. You should know it by heart because it's very common reaction in chemical engineering. What is it? It's the water gas shift reaction. It's the water gas shift reaction, and this reaction is carried out in a reactor at 827 degrees C and 10 bar. Actually, I got this example from your Thermodynamics book, Smith and Van Ness, chapter 13. We're talking about equilibrium. So we start the reaction with 1 mole of CO, 1 mole of H2O, and 1 mole of CO2, and 0 mole of hydrogen. Thermodynamics tell me, well, this reaction has a delta G, standard delta G, that is negative. That means the reaction is spontaneous. So it will proceed forward. It will happen spontaneously, right? So it will happen spontaneously and will keep going forward, right? Until, if I give it enough time, for equilibrium to be reached, until the equilibrium composition is reached. What is that equilibrium composition? Well, it is this way. It is 0.67 mole of CO, 0.67 mole of water, and 1.33 mole of CO2, and 0.33 mole of hydrogen. That means that the equilibrium conversion is 33%, right? It's 33%. That's the equilibrium conversion. No matter how long I wait after that, I will not get more conversion because that's the equilibrium conversion. That's the maximum achievable conversion. Correct? Okay, how can I calculate this composition? How can I calculate this composition? Well, if we talk about equilibrium, then we can always go back to thermodynamics, right? And use the equilibrium constant to calculate the equilibrium composition of this reactive mixture. Or we can calculate the equilibrium conversion. But the question is, how long should I wait in order for this composition to be reached, in order for this equilibrium conversion to be reached? How long should I wait? Or if we have a continuous flow system, meaning I'm continuously feeding 1 mole per second CO into the reactor, 1 mole per second of H2O into the reactor, and 1 mole per second of CO2 into the reactor, then how long the reactor should be, how big the reactor should be, so that at the exit I'll have the equilibrium composition, or at the exit, or by the exit, I'll have reached the equilibrium conversion. How long the equipment, or how big the equipment should be. Okay, so to approach this equilibrium composition or conversion, the question is, how long should I wait if we have a batch reactor, or how big the reactor should be if we have a continuous flow reactor? How can I calculate this? Well, this is not the business of thermodynamics because it depends on rate, the rate of reaction. What is it the business of? It's the business of chemical reaction engineering. Okay, so now I think the picture is very clear to you about the core subjects of chemical reaction engineering and what each subject teaches you, or what each subject enables you to calculate, and what's the limitation of each subject. Okay, so now you understand that thermodynamics always tells you about equilibrium and equilibrium calculations, right? It sets the limit. Well, at this condition, the maximum conversion that you can achieve is 33%. How did you know? By the knowledge of thermodynamics. So that's because it deals with equilibrium and it sets the limits. Okay, however, how long should I wait until I reach equilibrium, or how long should I wait until I reach a given conversion, right, or a given temperature in terms of heat transfer, or a given concentration in terms of mass transfer? How long should I wait, or how big my equipment should be in order to achieve that status, that depends on rates, right? That depends on rates, and the rates is not the business of thermodynamics. The rates, if it was a physical process rate, then it's the business of transport phenomena. If it was a chemical process rate, then it's the business of chemical reaction engineering. Okay, we'll meet soon in segment 2.